All right, let's dive right in. Today, we're pulling back the curtain on the math behind one of the most mind-bending theories in all of science. We're going to explore the strange, beautiful, and elegant rules that are the absolute bedrock of quantum mechanics. So, to kind of get our heads in the right space, let's start with a big question. If the entire universe were a book, what language would it be written in? Well, when you get down to the deepest, most fundamental level, the quantum level, that language is pure mathematics. And you know, it's not meant to be a barrier, it's literally the only way to accurately describe the reality of the very, very small.
But here's the first huge twist. This is not the kind of math we're used to, the kind that gives you a nice, certain answer. Nope, at the quantum scale, the universe speaks in the language of probability, and that is the single biggest mental shift we have to make to even begin this journey.
I mean, just look at the difference. It's like two totally different rulebooks for reality. In our everyday classical world, a baseball has a very specific position and a very specific momentum. We can predict its path, no problem. But in the quantum world, an electron is more like a smeared-out wave of possibilities. Its properties aren't fixed at all until we look. They only exist as a set of probabilities.
So, to help us navigate this completely new reality, here's our game plan. We'll start with the main character in our story, the wave function. Then, we'll figure out how we ask it questions using things called operators. After that, we'll see how it changes over time with the legendary Schrödinger equation. And finally, we'll zoom way out to see the grand mathematical stage where this whole show takes place.
Okay, let's get into it with our very first and maybe most important concept, the thing that actually describes a quantum state. You gotta forget about tiny little billiard balls. We need a whole new kind of tool for this.
And here it is. That tool is called the wave function, usually shown with the Greek letter psi. Just think of the wave function as the ultimate biography of a quantum particle. I mean, everything, absolutely everything you could possibly want to know about that system, its energy, position, momentum, it's all bundled up and encoded inside this one single mathematical function.
Now, here's where it gets even more interesting. Wave functions aren't made of just regular old numbers. They absolutely require what we call complex numbers. These are numbers that have both a real part and an imaginary part. And this isn't just some weird mathematical choice for the fun of it. It's essential. It's the only way to properly describe the weird wave-like behaviors of particles like interference, which is a total hallmark of the quantum world.
So, you might be wondering, if the wave function itself is this abstract mathematical thing, how do we connect it to the world we can actually measure? Well, we use a simple but totally profound recipe called the Born rule. It's a three-step process. You take the wave function, psi. Then you do a little math trick and calculate its absolute square, which always gives you a real positive number. And just like that, what you get is the probability of finding that particle at any specific spot.
And this leads to a really important rule. If you add up the probabilities of finding the particle at every single possible point in the entire universe, the total has to equal exactly 1. It just has to. This is called the normalization condition. It's basically the math's way of saying, look, we're 100% certain the particle has to be somewhere. Okay, on to our next building block. We have this rich, complicated wave function, but how do we actually pull information out of it? How do we ask it simple questions like, hey, where are you? Or how fast are you moving?
We do it using things called operators. An operator is basically a mathematical machine that stands for a physical question. You want to know the position? You feed the wave function into the position operator, it does its thing, and it gives you information about where the particle is. It's like a question machine for the quantum world.
But, you know, there's a really critical rule here. If this math is going to describe our reality, then the answers it gives us for measurements have to be real numbers, right? I mean, you don't go into a lab and measure a position with an imaginary number. That's where a special type of operator, a Hermitian operator, comes into play. Their one superpower is that they are guaranteed to always spit out real numbered answers.
And what's so cool is that we can see how our familiar, everyday physical ideas get mapped to these mathematical tools. There's a specific operator for position, a different one for momentum, and one for total energy, which is so incredibly important it gets its own special name, the Hamiltonian.
So what's the actual number that pops out of one of these measurements? Well, in the language of quantum mechanics, that specific result is called an eigenvalue. And here's where your brain might start to hurt a little. A particle is usually in a mix, a superposition of many possible states. The very act of measuring it forces it to pick one. But if a particle is in a special state where a measurement is guaranteed to give one particular value, like a definite energy, we call that an eigenstate.
Okay, so we've got a handle on what a quantum state is, and we know how to measure its properties. But what about the biggest question of all? How does that state change over time?
The answer to that question lies in what is, without a doubt, the most famous and important equation in the entire theory. This is the master rulebook. It dictates the entire, beautiful, complicated dance of the quantum world from moment to moment.
And here it is, in all its glory, the time-dependent Schrödinger equation. This thing is the engine of quantum mechanics. On the left side, you've got how the wave function changes with time. And what's telling it how to change? That's the right side, the Hamiltonian operator, the total energy, acting on the wave function. So, in a nutshell, what this says is, energy dictates how things evolve.
Now, while most wave functions are evolving in all sorts of complex ways, there are these special, superstable solutions called stationary states. These are just the eigenstates of the energy operator. For a stationary state, the basic probabilities of where you'll find the particle, they don't change over time at all. If you want a real-world example, think of the stable energy levels of an electron inside an atom. Those are perfect examples of stationary states.
All right, for our last piece, let's zoom all the way out. We've seen the individual parts, the wave function, the operators, the equation for evolution. But what's the grand, elegant mathematical structure that holds this whole thing together?
It's called Hilbert space. Think of this as the grand arena where all of quantum mechanics happens. Now, don't picture it as a physical space like your room. It's a completely abstract mathematical stage. Every possible state a particle could ever be in, every possible wave function, exists as a single point, or a vector, in this gigantic, often infinite-dimensional space. The whole quantum drama plays out right here.
So really, everything we've talked about can be boiled down to these 5 core rules. States are just vectors in Hilbert space. Things we can measure are Hermitian operators. The results we get from measuring are eigenvalues. The chances of getting those results come from the Born rule. And how it all changes is governed by Schrödinger's equation. That's it. That's the complete mathematical playbook for quantum mechanics.
And this incredible framework leaves us with one of the deepest, most profound questions in all of physics. If the math, our only reliable guide here, only tells us the probabilities of what we might find, what can we possibly say about the reality of a particle before we look? Is it actually in all places at once? Or is our amazing theory somehow still incomplete? And that, right there, is where the physics ends and the philosophy truly begins.